Okay, today's lesson we are going to discuss about the main algorithm that is used for machine learning, which is gradient descent. We have discussed how a machine learning algorithm, uh, especially when it comes to linear regression, there are two ways that we can solve the linear regression problem. One is using uh, a direct solution, right? Uh, and which is not using a technique known as the normal equation, which belongs to the closed form of the equation, which is a matrix equation. So we will be letting you about that matrix equation as well, right? So it is like it's like the uh, exact solution for a linear regression problem, but uh, when it comes to practical problems, when we have a lot of data, uh, you can't use it because the computational complexity gets exponentially increasing for the solution of that problem. Because of that reason, instead of using closed form solutions, so this closed form is a generic term which is used for taking the exact solution for a optimization problem like that, right? So instead of using closed form solutions, you can use iterative solutions, right? Iterative means you execute a certain rule again and again iteratively until you get to the final solution. So that is a so if you have learned about the subject called numerical methods, you might have learned about some techniques like Newton method, Newton-Raphson method, uh, bisection method, and so on, where you can use the use the empirical data. That means you can look at the numbers and you operate a certain update rule and you update the values, and after some time you can computationally approximate the final solution. So the problem we have is an optimization problem, and what we are going to do is we are iteratively execute a certain set of rules so that it would arrive to the optimum solution, not the exact value, right? So it may come to the exact value or it not may not, right? So you can approach to the exact value to a sufficient level of accuracy using these iterative methods. So the most widely used iterative method in machine learning is undoubtedly the gradient descent algorithm, right? So that is why we have given this whole lesson we have dedicated for the specific algorithm, right? So this algorithm is very important because this is not only used in uh, this where it is a simplest version of machine learning algorithm like linear regression, but also when it comes to neural networks, like if you have heard about ChatGPT and other large language models, or almost any type of current artificial intelligence system, most of them are using gradient descent algorithm, which is the algorithm that we are going to learn today. Right? So because of that, understanding how the fundamentals of machine learning works in real world, you have to know this algorithm so that you have the understanding how the things are working in the machine, uh, other than the statistical foundations that you learn in this lesson, right? You learn in this subject module, right? So this algorithm is very important for you to understand. So before we start it, so just remember that this may need some knowledge about calculus if you want to understand this exact algorithm that we are using, but this is not necessary. Having a basic understanding about calculus or differentiation basically is sufficient. And the partial differentiation is nothing big different from nothing big different from the ordinary differentiation, right? So the partial differentiation is you are taking the differentiation with respect to a single variable. So even if you don't know about differentiation at all, right? So differentiation is actually taking a you take a function and you look at the slope at each of the point, right? So you draw a line touching the so we'll start it like this, right? So that you guys can uh, understand from the beginning, right? So for example, so this is how we are going to start the lesson. So you may be thinking, why is this? So this is necessary because the knowledge about uh, machine learning is not relevant to this algorithm, but it is mainly uh, it may be relevant to the knowledge about this calculus. So because of that, I will let you know in simple terms. So if you have a curve like this, you can draw a line touching to this curve in this certain point. So the slope of this line, so this is the angle between of this line to the horizontal axis. So this is known as the slope of this curve at this point, right? So this is also known as the derivative or the differentiation of this curve at this particular x value. So this is x and this is fx, right? When it comes to this curve, the differentiation of this curve at the point x1 is the slope of this curve at that particular point, right? This is basically the differentiation of the curve. So let's move to the things we know, and we can extend from uh, this knowledge how we are going to apply this algorithm to linear regression, right? So basically, when it comes to linear regression with multiple uh, variables is basically having multiple x variables, which are independent variables, and you find a certain y variable, which is having a linear relationship between each of these x variables. So in that case, we can use a linear regression. So when it comes to two-dimensional linear regression, you can have a curve like this. So when you have data like this, right, you can draw a curve fitting these data points. So there is only one x value, which is x1, but there can be multiple uh, x2, x3, and multiple dimensions, right? We can't actually draw those dimensions in the 2D space. I am just trying to explain, right? So you can't draw these lines because you can only draw only two x value, right? So this is the y value, right? So what we are going to try to do is we are going to find this line, the curve of this in the multidimensional vector space, right? So when this is on, there are only two dimensions like x1 and y, we can draw a line. But when it comes to multiple x values, we have to draw not a line like this, but a hyperplane with multiple dimensions, actually one lesser than the total number of dimensions here, right? So in this case, there are 1, 2, 3, 4 dimensions. Then the hyperplanes would be something like this, which is having a three-dimensional hyperplane, right? So this suppose this is a hyperplane. So this should be a three-dimensional hyperplane. You can't draw a three-dimensional hyperplane in this two-dimensional space, right? So you may see it as a two-dimension, but it is a three-dimensional plane, right? So basically, what we are going to find in the linear regression is to find this three-dimensional hyperplane, which should be represented by this uh, relationship, right? Where you have, which is a linear combination of beta values and the x values, right? Basically the beta vector and the x vector. So in this case, it would be x0 vector, which is 1, right? So we don't write it here like beta 0, 1, beta 1 x1, beta 2 x2, and beta n xn. This is the y value, right? So what we are going to do in the linear regression is we are going to find the beta values in this equation for while reducing the error, right? We want where the error is minimized. We want to find these beta values. So when we find the beta values, this is what we want as the solution of the linear regression, right? So in order to find the total errors, we use mean square errors, right? And also we discussed that when we are having a nonlinear relationship between x and y, we can use nonlinear transformations to these x variables like the polynomials, and then you can model it, right? So however, the idea is that these x values are beta values are having a linear relationship, and we want to find the beta values so that the errors, the total amount of error is minimized, right? So in the so the idea is that we want to minimize this error, right? So this is the label value, or which is known as the ground truth y label, right? So this is the predicted y value, right? So y hat. So the difference is given by the error, right? So denoted by epsilon. So this is the when we are using the beta parameters for x variables, this is the predicted value, right? So this is the beta vector. So in order to find this beta vector, right? So the objective of the linear regression is to find the beta vector. So there are two ways that we have already discussed. One is using the closed form, using the normal equation, right? Where we can directly find the beta parameters like this, right? So you can get these are matrices, right? So you can, these are vectors, right? So you can use the xt, that x transform x, and take the inverse of it, and then we multiply it with the x transform again and multiply with the y vector, right? So this is how you can directly get the beta values, right? So this is the closed form of linear regression. So you may think that so now it is easy, right? So why do we need any other algorithm like the gradient descent? But the problem is now by looking at this equation, you can see there is a inverse matrix operation, right? So xtx inverse. So this inverse is a matrix inverse operation, which is uh, very expensive when the uh, size of x is too large, right? So taking an inverse matrix is very difficult when you are having a larger matrix, right? So when you have a lot of parameters, and so then uh, this would not be easy, right? So because of that, normal equation in the closed form can be used, but it is not practically used, right? So instead, we are using the iterative technique known as the gradient descent in most of the cases, right? So in the gradient descent, you can exactly get the beta values, but you can uh, do do a certain apply a certain rule again and again. Then you can approximate to you can more come to come to a near solution near to the close to the exact beta values, right? So with using this gradient descent, you can actually solve most of the uh, machine learning problems we are dealing in today's world, right? So that is why it is very important to learn this gradient descent algorithm. So first, look at the how the uh, simple linear regression uh, is represented, right? So in the simplest form of linear regression is not the multiple linear regression, but the simple linear regression, right? So when it comes to simple linear regression, we have f beta x, right? So in the earlier time we might have not discussed about this beta. Beta is about saying that this function fx has parameters represented by beta, right? So these parameters are in the simple linear regression, it may be beta 0, which is the intercept, and beta 1, which is the gradient, right? So of the line, right? So you may have learned, right? So in the when it comes to a simple linear regression, you have only one x parameter and fx or f beta x, right? So in simple terms, let's say fx. So we want to, when we have data, we want to find this line. So the intercept is the place where this is beta, right? Sorry, beta 0 is the intercept, and this gradient is given by beta 1, right? So what we want to find in the simple linear regression are these beta 0 and beta 1 values, right? In order to see, so we want to find beta 0 and beta 1 values while minimizing the errors uh, of this line from the data points, right? So we can represent the error with respect to these beta values using a function known as j beta, right? So like here we are representing a function of fx where the x is varying and we are finding a certain value. In this case, we are using these beta values or the parameters, and we can use the beta parameters as the arguments and get a function uh, of errors known as j beta, right? So this is a convention when it comes to machine learning. So we want, so this it is like the fx, right? So here what we do is we have parameters in, this is a 3D plot, right? So we have uh, like which is this is beta 1 and this is beta 0, right? So when the beta 1 or beta 0 are varying, we can see how the j beta is changing, right? In this case. So in simple linear regression, the uh, simple linear regression, you can see the curve between the beta 1 and beta 0 are as follows, right? You can see this is like an inverted hammock, not a hammock, it's a inverted ball kind of thing, right? So like a hammock, right? So yeah, you can sleep in this curve if it was built with cloth or something, right? So there's a bottom which is covered, right? Uh, and it is like, so this has a one minimum point and no other local minimas, right? So local minimas means something like this, right? So sorry, if we have a curve like sorry, if we have a relationship like this, and if we have curve like this, there are multiple minimas, right? Minimum points. So if you try to see uh, the minimas, minimum points, you can see this is a minimum point, and this is also a minimum point, right? So there are multiple minimas, but in this curve, you can see there's only single minimum point, right? This point. So this is another advantage of using the linear regression, where there's only one single minimum point. So, but when it comes to complex machine learning algorithms like deep learning, there can be multiple minimum points in the curve, right? So in here, we don't have to consider about these things, right? So we are just looking at this linear regression and how it can be uh, solved using gradient descent in this lesson, right? So this is just an example, right? So you can use this gradient descent for other algorithms as well, but because we have learned about simple linear regression, here we are learning about how to using the gradient descent to solve the linear regression problem, right? So this is a 3D visualization, right? So we are going to see how to solve this problem. So the problem is that we want to find this exact beta 0 and beta 1 values, uh, which is minimizing this j beta value, right? So when it comes to the j beta, which is that means we want to find the minimum point of this curve, which is this point, right? So we want to find the uh, beta 0 value and beta 1 value uh, of this at the point where the j beta is minimized, right? So in this case, it is 0, 0, but generally it may, yeah, it may be any point, right? So it can be 5, 3, 8, 6, or whatever the number, right? So when it comes to beta 0 and beta 1. So when it comes to this iterative process, right? So I said that when it comes to finding the optimum value for beta 1 and beta 0, uh, in the iterative way, we start at some point and then we iteratively uh, set some values for beta 0 and beta 1, and then we execute the same rule again and again until we find that uh, the error is minimized, right? So or minimized, or you can't go further. Then only we stop it, and then we take the values for beta 0 and beta 1 as the optimum beta 0 and beta 1 values, right? So that is what we are going to do in an iterative uh, algorithm like gradient descent, right? So gradient descent is one of the iterative ways of finding the optimum value for a curve like this, right? So there are several ways of initializing the values for beta 0 and beta 1, right? So in order to go to the optimum value, we have to start from a certain point, right? So we have to start somewhere, and from that point we can look at where the gradient is, where the j beta. So in this horizontal axis is j beta, right? So although we have not numbered it, so we want to find where the j beta is minimized, right? So like we can start somewhere and we can move to another point where this one is minimized, j beta is minimized, and then in the next iteration we move another small uh, change for beta 0 and beta y, and move to another point and another point and another point until we move to the optimum point, right? So the idea is we want to minimize the j beta. So once we go to the final value, then we take the beta 0 and beta 1 values, and then we can say, okay, these are the optimum values for beta 0 and beta 1, right? So in order to do that, we can start somewhere. So somewhere is where to initialize the values for beta 0 and beta 1. The first way is the most common name, which is known as the random initialization, where you can get some random value like this one, right? So we can have this x value, sorry, beta 1 value, and this beta 0 value, right? So somewhere here. So this is the beta 0 value, and this is the beta 1 value. We have selected some random value, right? So this is known as the random initialization. Or you can start from zero initialization. But in this case, so this is because this is a special graph. So if you take the zero initialization, this is the solution, right? So don't think about that, right? So solution may be anywhere, right? So you can take the zero as the initial values for beta 0 and beta 1 in the zero initialization, right? Or either you can use random values like 3.58 and 3.58 for beta 0 and 8.6 and 9 for beta 1 and so on for initialization, which is known as random initialization. Or you can set beta 0 equals to 0, beta 1 equals to 0, is known as the zero initialization, right? Then we can, wherever we have started, then we can iteratively move to the optimum point where the J beta is minimized. So actually the idea is that we move at the direction where the J beta is minimum, step by step, right? So you may think, why can't we simply move to from this point to this point in a single step, right? So the idea is that we don't know the exact formula for this in this equation, right? So we know the equation, but because this is a simple linear regression, but although it is not practical to calculate it using the closed form, right? So, but when it comes to machine learning, there can be different formulas, right? Different functions which may have very complex curves, not like this one, right? So we don't know the exact formula of this curve, right? So because of that, we don't know how exactly we can move to the optimum point, right? So if you know that point, so then we can simply get this one, right? So but because that is not practical, we have to move from step by step. Otherwise, if we move too fast, we may not stop here, but we may move to some other place, right? So in this case, you would go from here to here, somewhere else, right? Not to the optimum point. Because of that, when it comes to these iterative methods like the gradient descent, we move in smaller steps. We move. The idea is that we are moving towards the solution. Even in smaller steps, with large number of steps, we can go to the solution. Right? That is the idea of using the these iterative methods. Right? Where the cost is getting minimized. In order to simplify the same thing, right? So because the 3D plot is a bit difficult for explanation, where there are beta 0 and beta 1, I have just taken 2D graph where there's only one beta value, with like the independent variable and the J beta as the cost function, right? So suppose we start from here, right, as the initialization point. So here what we do is we are going to draw a line touching this particular curve, and then we can find the angle between the x-axis with this particular line, and this is the slope or the gradient or the derivative of this curve at this point, right? So the slope of this curve, or the tan theta, actually not the exact theta but the tan theta, is known as the, if you know about mathematics, it's known as the tangent of theta, right? So this line is known as a tangent, right? So which is touching that particular curve. So this is a tangent. So this value, you take the theta value or the angle, and we take the tan value. So it's the tangent value. So this slope is known as the tan theta of this curve at this particular point. And we are going to reduce. So because this theta is a positive value, if you know about trigonometry a little bit, so you may know that if theta is larger than, so theta is like that, right? So between 0 and 90, you can see that the tan theta is a positive one, right? So because of that, this gradient is a positive gradient, right? So the optimum way, what is the optimum point? So the optimum point is where the j beta is minimized, right? So we want to find the beta value where the j beta is minimized. So j beta is minimized and find the optimum beta point. So this should be the optimum beta point, right? So our idea is to, our objective is to come to this particular point. Uh, so in this particular point, what is the tan theta? So you can write a tangent to this particular point, and you can see the angle between this x-axis or the beta axis to the this particular curve is 0, right? So the angle between this tangent and this axis is 0 because they are parallel, right? So you can see when the tan theta is 0, it is 0, right? The gradient is 0. So that means when you are at the optimum point, the slope, tan theta, gradient, or derivative all are pointing to the same thing, right? Those are equal to 0, right? So actually not only, so the tan theta is 0, the gradient is 0, doesn't always mean that you are at the minimum point, right? So even if you are at a curve like this, right? So uh, in this point also, the tan theta is or the slope or the derivative of this curve is 0. But this is not the minimum point, so this is a maximum point, right? Even if you have a curve like this, right? In this point, you can find that the slope is 0, but this is not either a minimum point like this or a maximum point like this. This is known as a saddle point, right? So those are related to mathematics, but we don't have to know all those things. But just for the clarification, I have just explained, right? For the completion. So the idea is that, so whatever, but you have to know is that you calculate the gradient here. If it is a positive value, because now this is a positive value, that means the tan theta is positive means the current beta value, which is this value, right, is greater than the optimum beta value. So this is the optimum beta value, right? This is the current beta value, right? So we want to reduce some amount from this point to move to the optimum beta value, right? So the gradient is greater than 0 means we have to reduce some value from this point, from this beta value, to uh, get closer to the optimum beta value. Right? This is what we are trying to do in the gradient descent algorithm. Right? So this is known as the gradient, and we are moving in the direction where the gradient is descending. Right? We are moving to the direction where the gradient is descending until it comes to the it comes to 0, right? Or very close to 0. That is all about this gradient descent algorithm, right? So these are the initial values, and we in the first iteration we move from here to here. A small change we have taken for the values of beta, and now we are at this point. And in the next iteration, we draw another tangent, and we find still uh, the the angle is positive, right? So sorry, I have I think, let me erase it, right? So this is the angle, right? So now the angle is bit lesser than this gradient value, or the tangent is bit lesser than this value, but still it is greater than 0. and we are moving in a direction again to this point, smaller change in the beta value, and then we draw another tangent, and then we find now the gradient is even reduced, but still it is greater than zero, and we are moving a little bit uh, closer to the uh, to the optimum point by moving left, right? So then we move from here to here and come to this point, and again we come to this point, then we come again to this point, and finally we would end up here after many number of iterations, right? This is all about the gradient descent algorithm. So let's see how to quantitatively do the gradient descent algorithm, right? So although we can say that we can do it, but this is how exactly what we are going to do, right? So here, let me, okay. So here we can say we iteratively move to the minimum cost point. You can see the gradient is reducing and goes to zero, right? So this gradient is also known as the derivative or the slope or the tangent of the tan theta, uh, where the theta is the angle between the positive direction of the beta value and the curve, the tangent, right? Uh, or so this derivative is known as the slope of the curve, right? So the slope of the curve uh, at the point of beta is not in the when the parameters are defined by the beta vector, so, right? So this when there's only one beta value, the slope is given by this derivative, right? So or the j beta should be differentiated with beta, right? So once you differentiate the value of j beta curve with respect to beta, you get the derivative. Basically, this is equal to the, so if you are not familiar with calculus or anything, don't worry, right? So what you have to remember is that this value is equal to the slope, right? Or the derivative, which we want to calculate, right? So this value is what we are considering. dj dj beta divided by d beta, sorry, right? So but this is when there is only one beta value, right? So this d and d are given by the given as the differentiation, right? Right. So when it comes to full differentiation, this is how we represent the uh, slope of or the derivative of the curve, right? But when it comes to the real world problems, for example, in the simple linear regression, we have beta 0 and beta 1, right? Where there are more than one beta values. In that case, because there are more than one beta values, we can't write the derivative or the slope of the curve in this notation, but we use, which we call it as the partial derivative, and we represent the partial derivative of the curve with respect to the beta value using this notation, right? So instead of this d, we use this Greek character daba, right? So which is this known as daba character, right? Daba letter. So don't worry, right? So this is also the this is the actual slope of the curve with respect to uh, a given uh, parameter, right? So we have a curve with respect to multiple parameters, right? If we take j beta is the cost curve with respect to beta 0 and beta 1. So if you want to find the uh, where the direction or the slope of uh, this curve with respect to beta 0, uh, so if you want to find the direction of or the curve slope with respect to beta 0, it is represented by j beta divided by beta 0. Right? If you want to find the slope with respect to beta 1, then it's written as beta, so j beta divided by beta 1. Right? So you don't have to worry about these terms, right? So because you may find these are very complex, but there's nothing complex, right? So what you have to remember is this is the slope of the curve, right? We are going to uh, change the values of beta 0 and beta 1 iteratively so that this j beta is reduced, right? By looking at this value, we are updating beta 0s and beta 1s again and again or iteratively so that the beta 0 and beta 1 are found where the j beta is minimized, right? So when it comes, so this is what I have explained earlier, right? So when the slope is positive, that means the beta value is higher than the optimum value of beta, like this, right? So when the beta value or the slope is higher than uh, 1, higher than 0, that means this value is higher than the optimum value, right? In that case, we have to reduce some value from current beta to bring it to the optimum value. So what we have to do is we have to reduce some value, right, from here to here to uh, bring it closer to the optimum value, right? So, but what is the value that you should reduce from beta? That means how much you should reduce. You know, right? So now the slope is positive, and you have to reduce some amount from beta to make it closer to the optimum value of beta. But how much you should reduce, right? So there are several factors you have to consider, right? First thing is it is better to use a value proportional to the derivative. This one. So this is the, as I said earlier. So don't confuse with this term. This is the slope of the curve, right? Or the derivative of the curve. So it is better to use a value proportional to the derivative because when you can see when the point is more away and away, this gradient is larger, right? Larger and larger. So when the gradient is large, you have to add some value which is proportional to the gradient, right? So this is not, this may be a fairly good assumption, right? So this is one thing that you have to do. But the number should be sufficiently small. Why do I say that? I said that first we can produce a value proportional to the derivative, this one, but it should be small too, right? So maybe you can directly reduce from this particular value, but it is not good, right? So why is not? So if you reduce a small value, you can come closer and closer to this optimum point step by step. But if you reduce a large value, right? So you may from here to here, somewhere here, something like this. This you will go to a non-optimum point, even passing this optimum value, right? So reducing a larger value is not good, right? You should only reduce a smaller value like this one, right? Because of that, what we do is we take this value and multiply this value with the smaller constant known as the learning rate, represented by this alpha, right? for that use, because we want to reduce only a small value in this direction, the same direction, proportional to this value. What we are doing is we are multiplying this slope with the smaller value known as the learning rate, represented by alpha, and multiply it with this slope, right? So we multiply the slope with alpha, and we take this value as the value that which we are going to reduce from the original beta, right? Not the exact value or a higher value, right? So because we want to uh, move slowly, step by step, right? So not at once, because if you want to move at once, you would move away from the optimum point, and so then we again, if you try to add the large value, then it would go further away from the original point, and this should move here and there. So which actually what you are doing is you may be moving away from the original point, so which is known as the divergence, right? So in here, what when we are doing in smaller increments, you can converge to the original solution. But if we are using a very large value for this large value, then you would be diverging or moving away from the optimum point which we want to optimize, right? So so we reduce the multiplication of these values. Uh, this slope, this is the slope, and this is a constant which is small, right? Very small scalar value, right? Which may be equal to whereas alpha is a smaller value like 0.01. Sometimes people take 0.05 as well, right? So 0.01, 0.05, some value like that can be used for, you can select this value randomly, right? So randomly means you can guess some value and use it, right? So actually, when you are optimizing the models further and further, actually you can use better values for alpha. You can actually find several values for alpha and find which is the best value for alpha, likewise, right? So if you are not getting good results, you can use different values for alpha and check them, check different values for alpha, right? So those are known as hyperparameters, right? This alpha or the learning rate is known as a hyperparameter, where this beta are parameters, right? So parameters uh, are the variables which we are learning, right? Right? Hyperparameters are the values that the user or the data scientist or the data engineer or analyst is setting manually with his knowledge, right? So this alpha is such a parameter, which is the learning rate, is a hyperparameter where you have to set it by your knowledge, right? So now in the gradient descent, the update rule happen in one iteration can be given by this formula, right? So this is all about gradient descent, right? So what we are doing is we take the original, so we update the beta value so that from the original beta value we reduce some value proportional to the uh, slope, which is multiplied by the, so actually we take this derivative, the slope value, when we multiply it with this constant value, which is a smaller scalar value like 0.01 or 0.05, and then we reduce it from the beta, right? So uh, this is what we do in each iteration of the gradient descent algorithm, right? So this is known as the update rule, right? So how long should we apply this iteration? So once we initialize the values for beta, we can iteratively update the values of it until the cost function shows no significant reduction, right? So that means for each beta values, we can calculate the j beta values, right? And we find whether the cost is reduced. So in each iteration, we find the cost is reduced, and again. And then we find that if you find that there's no significant j beta reduction happened in the in this step, right? So we won't further uh, do these iterations again, and we take the values for the beta as the final values for the beta, right? So these will be the solution, the linear regression. So here we have explained for a single beta parameter, right? But you can have multiple beta values, uh, because there can be this beta can be a vector with multiple parameters, right? So in this case, you actually when we are using daba, that means we are assuming that the beta is having multiple values, right? So because we are we are taking the differentiation or derivative at a certain point of beta, right? Like for example beta j for that particular uh, parameter, right? That is why we are using partial derivation, right? Partial differentiation, because we want to take the derivation at a single uh, parameter of beta, right? So here is the exact way how we are calculating the. So this is the this maybe seems bit uncomfortable if you are not a maths if you are not having a math background, right? So but be with me, right? So this is not that complex, and although even if you don't understand what we learn in this slide, don't worry, it won't be a problem. So what we have learned up to now is sufficient, right? So here you can see the cost or the j beta is taken like this, right? So this is a variation of the mean square errors, right? So actually so in order to take the j beta value, we take a variation of mean square error, which is where we take the error and take the square and sum for the all the data points and divide by n, right? So this is the mean square error, but instead of dividing by n, here we can 2 instead of n to divide, right? So this is the j beta value that we have taken to make the things easier, right? For mathematically coming into solution, right? So when you come up with this kind, because this is the function of this is the cost function, right? The cost function is the total error that you get, right? So for each iteration, right? Uh, because this cost function uh, curve is actually a ball-like is having a ball-like shape, you can get only a single optimum value, right? So not multiple values. That means there's only a single global single minima, or the a global minima is only is equal to the minima, right? All there are no multiple minimas. Minimas means, as I said, there are no multiple minimum values because this is a curve given by this j beta. So we will see what is the differentiate. So what is the derivative of this j beta, which is given by the uh, slope of this curve, right? So this is the curve, right? And for a simple linear regression, we will be having a ball-like structure, uh, something like this, a curve like this would be there for a simple linear regression, represented by this equation, right? So let's find, so as I said, when it comes to partial derivative, we take a single parameter. That means if you, because you have multiple parameters like b0, beta 0, beta 1, beta 2, beta n, we can take a single parameter, beta j, and you take the partial derivatives. So if you don't understand, don't worry, right? About the partial derivatives, if you don't know, just forget about these terms from here to here, right? So just forget, right? Don't worry about it. If you understand, just this, I have just given this calculation for the people who know about partial derivative to get the knowledge about it, right? So for the completion, right? Mm. And here what we do is we are trying to take the partial derivative of this j beta with respect to the parameter value, right? So here what we do is, so if you know about the derivative differentiation, this is the function, and what we are going to do is, so let me put this one, right? So this is the function. What we are going to do is we are going to take the partial derivative. So what we do is first we take the power of this 2 and multiply with this term, right? So the 2 times half of this value, right? This value, right? 1/2 sum of 1 to n y hat I minus yi is the error to the power. This 2 is reduced to power 1, right? Here the power is 1, right? And it is multiplied by the derivative this of this term, right? Which is inside this uh, square, right? So it is yi hat minus yi partial derivative of beta j, right? So taking this one's derivative and taking so this is a power of something, some function, and we take the power of this function and taking the inner values derivative. So this is known as the chain rule in calculus, right? So that is how we have taken this value, right? So what we do is, so if you don't understand, or just forget it, right? So we take 2 times half of this value without by taking reducing the power from 2 to 1, and then we take the derivative of this term, right? So by this yi hat can be replaced by uh, its value, which we have already learned, which is the yi hat is the predicted value of predicted label, right? So which is equal to beta 0, beta 1, beta x1, beta 2, x2, and just forget it. And there would be some beta j value as well, right? So beta j xj and beta n xn, right? So we have just expanded this term, right? With this set of uh, terms, right? This is all we have done. So this two is getting cancelled, right? So only one is will be there. So this term would be remaining as it is this one, and this dabba by dabba beta j is there, right? This would be there, and this term would be replaced by this set of terms. Yi is here, right? So now what happens? We take the partial derivative of each of these terms, and when you take the partial derivative, if you know about it, you know, right? So if all the terms that are not having beta j terms, that means in these terms you can consider all of them as constant, and you can cancel all other terms like this term, this term, this term. In this term we have a beta j. We can also cancel out this term and this term as well, right? So only this term would be remaining. So this one's partial derivative is the multiplicating factor of beta j, which is xj, right? So we have taken this xj. So I have added denoted it as xij because this is for the ith data point j parameter. This is the variable, right? That is why I have just changed the notation from here xj to xij, right? So you don't worry, right? So I've changed from xj to xij just for making them compatible with the other terms, right? So that you can understand. So what's there is that you, so yi hat minus yi means the error multiplied by the uh, that means for that particular data point, and for the ith data point, and we multiply it by the ith data point uh, jth variable x, right? And then we add for all the data points because there are n data points. Sorry, not data points. Yeah, for yeah, for in data points, right? And this is the uh, partial derivative of uh, cost function with respect to the that particular parameter, right? So you can take it for so this is how we, so first we explain that this is the update rule, right? And n is the total number of data points, and for all of the uh, so wait a minute. So then what we are doing is we are going to replace this derivative term or the slope with the value that we have just found, right? So this value is the new term for j beta by dabba j beta by beta j dabba beta j, sorry dabba j beta by dabba bj, which is this term. We replace this one, we replace this term with this term, right? This is the real update rule, right? And we can do it for all the j values or all the parameters, and then you can update the values, right? Beta values likewise. We have here given the value how to update it for a single parameter, single j parameter, like 0 beta 0, beta 1 to beta n. You can apply this update rule in each of the iteration, and then you can have multiple iterations until you move to the optimum point, and then you can stop it. And the values that you have for each of the beta parameters is the final values of the final values that we wanted to calculate, right? So if you want to take the summary, what we have done up to now, right? So what we have done is we have initialized the beta j parameters. Either you can initialize them with 0 values, or you can initialize them with random values, right? So you can have generate some random numbers and set them thing, right? That set these values for values of beta j's like beta 0, beta 1, beta 2, and so on. And then we manually set some value for the learning rate alpha, something like 0.01. And then we start this algorithm where we applied this uh, update rule, what we have just found for each of the parameter beta j, right? For for that you would have to calculate these values for all the data points, right? So error times the variable value x variable, and we multiply it with alpha, and we reduce it from the original uh, parameter value, and that's how we update it until we come closer to the optimum value, right? And then stop the repetition when the cost function reduction is very little, right? So for each of these beta values you can find the j beta or the total cost, and if the total cost is not reduced, or almost there's no significant reduction in cost function, then you can stop the algorithm, right? And this is the finish of this algorithm, that now you have found the optimum values for, or the approximately the optimum values for the bj beta j's, or the parameters, right? And these are the values that we wanted to find in the linear regression. So the linear regression is finished, right? So that's how we do the linear regression using uh, gradient descent algorithm, right? Okay, now we have discussed how to solve the simple, or the linear regression using the gradient descent, and when we are executing the algorithm iteration by iteration, you can see the cost function, or the, in this case you can see, wait a minute, so this is the j beta, right? It's getting reduced, right, until we come to a stable value, right? So this is the minimum j beta that we want to achieve. So once we, in the earlier steps, we can see there's a huge reduction in j beta, and then the j beta reduction would be lower and lower, and then it would uh, get stabilized or saturated in a certain level, right? So you can't further reduce this error, right? So this error is caused by some other reasons. Because of that, you can't reduce this error. You have to satisfy this error with your current level of accuracy. So this is the maximum level of accuracy that you can get, right? So you know, right? The cost is the total error for the data points, right? J beta is this value, right? In a, in each epoch or the iteration, the cost is reduced with the reducing rate if the process is convergent, right? So the idea is that I said that you have to select the learning rate carefully, right? So only if you take a smaller learning rate, then you would be able to see the cost is getting reduced in each of the iterations, right? Like this. If it is getting reduced and again, that is known as converging, right? So if it is going to this optimum value, that means the uh, algorithm has converged, right? Uh, then it would have the error reduction would be insignificant and come to a certain this optimum value, right? Uh, this can be done. That means once you come to this optimum value, you can take this as the optimum value, because in linear regression, there are no multiple minimas, and there are no multiple minimas, local minimas, uh, as we discussed earlier, right? So unlike in the deep learning cases, deep neural networks, we won't have in this case, because we can safely say this is the best error, or the least error that you can get with the given set of parameters, beta 0, beta 1, and beta n, beta 0, beta 1, up to beta n, right? So these are the values that you can get with the least amount of error, right? In order to represent this three-dimensional curves, this is not related to machine learning, but this is about just data visualization, right? So if you want to represent a three-dimensional curve like this, you can take the contours, or you can connect the points where the same altitude are connected together. You can draw a contour curve. so on, right? So I'm not drawing it. So you can connect the uh, similar altitude points together, and you can draw a contour so that you can represent this 3D graph in a 2D manner, right? So in this way, you can actually uh, draw how the optimization has happened with different strategies, right? So that is why it is important. So now let's see uh, what is the effect of learning rates, right? Right. So I just said that the selecting the learning rate is a task for it's a job of the person who is running the algorithm, right? So he or she has to select the value for assert for the learning rate, like 0.01 or something like that. Uh, so how to select that particular number, right? 0.01 is a good value, generally used by most of the people, but when you have the opportunity to change it, actually you may have to run it several times to find a good value for the learning rate, right? And if you know, try to learn more about learning rates, or when it comes to these kind of algorithms like the linear regression and so on, you can use the constant learning rate throughout the learning process. But when it comes to complex learning techniques like deep neural networks, sometimes the learning rate is also getting changed uh, using some other techniques known as optimizers, right? So you might have heard about the momentum optimizers, ADA, adder grade optimizers, ADAM, ADAM optimizers, right? So with those optimizers, the learning rate is getting changed with respect to some other parameters. So we are not going to discuss it in this lesson because it would get much more complex, right? So the idea, and also uh, as a technique, sometimes you can programmatically change the learning rate throughout the session, right? So maybe you can start from a higher learning rate and then you can reduce the learning rate kind of thing, or you can increase it first and then reduce it, or different things people have published about changing the learning rates in some papers, right? So maybe you can refer them, but in general, when it comes to simple learning techniques like linear regression, you can use a constant learning rate. So you have to know what is the value that you should take for that particular learning rate, right? So if you take uh, so the idea of selecting the learning rate is so that the uh, learning rate wait a minute so that the model first thing is uh, the model should converge to a solution, right? So converge to a solution means it should come approximate and come to the optimum point and stay there, right? So not moving away from it and go around here and there and go away from the optimum point. So it should not diverge, right? It should go to the original solid. It should come to the optimum point and stay there. That is the idea of converging, right? So the model should converge. That is the first requirement of selecting the hyperparameter learning rate, right? And actually, you can select a very lower learning, very lower learning rate and make sure that the model is converging, right? Maybe you can select 0.001 and you can make sure that it is moving to the optimum point, but that is not the only thing, right? So, and you have to think about the training time as well, right? So if it takes thousands or millions of uh, iterations to come to the optimum point, so it is a waste of time and money and electricity, right? So it should come to the solution in a fair amount of time, amount of iterations, right? So you should not take a very low learning rate to make sure that it is converging because it would take much time to converge, right? So if you look at this uh, relationship, which is the number of iterations it takes for different levels of learning rate, and the cost is how the cost is getting changed, right? So the idea of cost is that the cost should be reduced and come to the optimum point, right? So this cost is basically think it as j beta, right? So it should be reduced and come to the optimum point. So if you select this very low learning rate, it would move very slower to the solution, but it would definitely come to the solution, but uh, it would take a lot of time to come to the solution, right? And if you take a very high learning rate like this, like the green one, it would try to come to the solution very fast. Unlike the very lower learning rate, it would come to the it would reduce the cost very fast, but after some point, it would not reduce its cost, right? Because it would uh, not stay at the optimum point, and it would run here and there, and that error would be there after you come closer to the optimum point. So this uh, error would not be reducing to the optimum error. So there should be a fixed amount of error remaining even after it is getting stabilized. But when you're using a lower learning rate, it would stabilize at a very lower uh, error, optimum error, but it would take a lot of time, right? So uh, that is one of the uh, trade-offs of using lower and higher learning rates, right? And if you are using a very high learning rate, it would not even so would be the very high learning rate. It would not actually converge, but it would diverge. Like it would move away more and more from the origin from the optimum point. So this is not suitable at all, right? So you should not use you should never use a very higher learning rate. If you find that your learning is too high, you can start or move to a lower learning rate and try, right? Right. So for when you're taking good learning rate, it would optimize both the uh, training time, right, uh, compared to the lower learning rate, and reduce it would reduce the cost further than the higher learning rate, so that it would come to the solution optimum cost in a fast way, right? So that is how you should consider which to be considered, which amount of learning rate to be selected, right? Uh, the that is the final cost would be affected when you are using a uh, that means if you want a very low final cost, you should use lower learning rate, uh, and if you want to move it faster, you have to use higher learning rate. So uh, param these are the conflicting requirements, right? So it should be a some learning rate which is in something in middle, right? So the two large learning rates have higher tendency for diverging, and two lower learning rates are trained slower, right? So we have to find the optimum learning rate, and this is how it happens, right? So if it is a very low learning rate, it would take a lot of steps to come to the optimum point. Uh, if it is a very larger learning rate, uh, it would not actually, because this reduction is very large, it would move from here to here, not to the optimum point, but even passing the optimum point from somewhere here, and then it would find, oh, now it is further away from this one, so it would move to the other side, add some value to the beta value, and it would even move away from the original, it would pass in the original uh, initial point, and it would be further away. So now it would find, it would even reduce a higher value from the this point, and it would move further away from the uh, furthest point that was there in the theta value, and it would move further away and away. So this is a diverging case, right? So if you take a lower learning rate, it would take a lot of time, but it would guarantee that it would come to the optimum point, but it would take a lot of time. If you use a very larger value, it would move away from it. So it is diverging. So if you take a correct optimum value, actually you don't know what is that optimum value. You have to run it several times and find it. If you go select a good learning rate, it would come to the point faster and with lesser error, right? At the end. So at the end, the effect of uh, error at the end is not explained in this case, right? So we'll try to, so in this case, what it has explained is how selecting the learning rate is affecting at convergence, right? So this learning rate is actually a compromise between high risk and faster convergence. So if you can select if you have a way to find the highest learning rate that can converge, this is the best one, right? But it is risky because it can diverge, right? This convergence happens due to oscillation, right? So now we have learned about the learning rate as well. So let's see the name what we have learned, right? So the algorithm what we have learned up to now is actually known as the batch gradient descent, right? So we have learned it as the just gradient descent, but its actual name is batch gradient descent. Why is that? You can say by looking at this update rule, right? So in each iteration, the updating rule is in each iteration, or we call it as the epoch as well, right? For the iteration. In each iteration, what we do is we reduce some value from the beta. So this value which we should reduce from the beta j has to be calculated using all the data points, right? So from I equals 1 to n, that means for all the data points, you have to calculate this error and this variables. So suppose you have 100,000 data points. So now n is 100,000. You have to, for each parameter update, you have to uh, add these errors multiplied by the x values for 100,000 times, which is very expensive, right? But the advantage is that, as we mentioned, that this would move to the direction of the optimum value, and it would guarantee, it would have, with the lower learning rate, you can make sure that it is moving to the correct direction, right? But when it comes to a very larger data set, like 100,000 or 1 million data points, this approach, the batch gradient descent approach, may be inefficient because calculating like a million times, calculating these values for each of the iteration is very expensive, right? So it consuming time and electricity and the computation power, which is mm, not very efficient, right? So instead of that, there's another form of gradient descent which is known as the stochastic gradient descent. Right? In this case, instead of adding these errors multiplied by the x variable uh, for all the data points, we take each of the data point and then we update the beta values for each of the data points, right? That means instead of taking the whole batch and adding all those things, we don't have the add symbol here, right? So we just take the error multiplied by the x variable and multiply with the alpha value, learning rate, and then we reduce it from the original parameter. In this way, if we have a lot of, there are many number of uh, data points, or there are many data points in the sample, but by the end of the, for all of the data points, if you do this should actually move very closer to the optimum values of the beta j's without much effort, like without much computation at calculating the values for all the data points, right? So that means for each of the data point, we can calculate this one and update these beta values, and you can select these values, select each of the data points one by one, and then update these values, and this would be very fast, comparatively faster and efficient uh, compared to the batch gradient descent uh, when you have a large number of data points, right? But when you have something advantageous, right? So there are some disadvantage in it as well, right? So, but in the stochastic gradient descent compared to the batch gradient descent, the disadvantage is uh, that there won't be the guaranteed convergence as given in the batch gradient descent. So if you select a very smaller learning rate, you can actually assume with high probability, you can guarantee that the solution would be converging to the optimum point. But when you are using a batch, when you are adding these values and add for all the data points, but when it comes to when you are updating these beta values for each of the data points, because these data points are uh, can be highly different from its total distribution. When you are updating these beta values, they would be actually moving away from the optimum points temporarily, right? So what I say is that if you update these values for each of the data points without considering the whole distribution, you may be updating these beta values in the opposite side as well, right? So sometimes you may update these beta values uh, that are not in the optimum way. But because we are using it for many number of data points, actually it would be finally it would be moving to the direction of the distribution. But when you are considering 1, 2, 3, or several number of iterations, it may be actually there's a there's a chance that it would be moving away from the distribution, and moving away from the optimum point as well, right? So this is not stable or uh, uh, smooth as gradient descent, batch gradient descent, when it comes to the optimization path, right? So we will see a graph in a future slide, right? But instead of having too much calculations, because this can converge much faster, the stochastic gradient is suitable for uh, when we are having a large number of data points, right? So the direction of updating for these beta parameters may not be in the direction of the distribution, but it may be a temporary one, right? And the other disadvantage is there's another disadvantage where when you come to the final point or the optimum point, uh, when you update when you are trying to do any update, because you are using a data point instead of the distribution, because this data points uh, can, can maybe, right, so would be different from the distribution. It would ask the uh, ask the values to be changed from the optimum point. So it, it would be very difficult. Actually, it would not. It may be impossible to move very closer to the optimum point when you are using a stochastic gradient descent, because it would uh, walk around the optimum point without coming into the optimum point, uh, because the data points are having different values, not the distribution. So different data points would say go to this direction, and the other data point would say go to the other direction, and so on. It would not come to the uh, optimum point, right? Because of that, that is another disadvantage of stochastic gradient descent. Instead of using now the problem of batch gradient descent is you are having high number of computation. You need a lot of computation to it. With the stochastic gradient descent is you the path would not be smooth, and the finally when you arrive at the optimum point, it would not go straight to the optimum point, and it would walk around the optimum point, which would have a final error. There would be a higher optimum error, which you can't reduce, right? That is the problem with stochastic gradient descent. So if you take something in between the batch gradient and the stochastic gradient descent, that would be better, right? So that solution is known as the mini batch gradient descent. So instead of taking the whole batch for finding the direction where the beta should be updated, you can take a small batch. That means you can partition your data set into small partitions, and each partition can be taken as a mini batch, not the batch, right? So the batch can be divided into mini batches, and each batch can be used for updating, right? So this is similar to the updating rule is similar to the batch gradient descent, but instead of using the whole batch, you are using a small batch with the size m, right? So if the total number of data points are n and it is equal to 100,000, maybe you can use a batch size of 100, so that you can get these values uh, added. And when you get 100 data points, most probably it would be pointing to the it would be representing the distribution, right? So because of that, it would be most probably pointing to the direction of optimization of the whole batch, so that it would do better uh, at uh, better at having smoother path to the optimum point than the stochastic gradient descent, or SGD, right? So stochastic gradient descent is also known as SGD. So this mini batch is better than SGD in that case, but still it would be having some uh, errors. It may be moving to the other directions than the optimum direction, because that mini batch may be uh, somewhat different from the full batch, but it can be used as a representation if the variance is the data are not having that much variance. You can use a mini batch. So generally you take the mini batch sizes m as 64, 128, 256, 512, 1024, and so on, so that it would those are some practical numbers, right? So you can select any number for m, so that it would work better, right? So in all practical cases, generally when you have a lot of data, stochastic gradient descent is possible, but minimal gradient descent can also be used for making sure that it is not diverging or having any issues with the final error higher, right? Something like that. Um, so that is the mini batch gradient descent. So by looking at this contour curves, you can see how each of them are converging. Like this blue one is the batch gradient descent. You can see how uh, smoother it is moving to the optimum point. And this is stochastic gradient descent in the purple color. You can see it is moving here and there. It's a very rough path. Sometimes it is moving away from the direction of optimum point, and it is moving here and there, then moving away from it and moving lateral sides, moving here and there. And even after it has come to the optimum point, it is not, it may be not coming to the optimum point, and but it is walking around the optimum point, because each data point may not be representing the uh, whole distribution. It may even at after we have arrived at the optimum point, due to some reason it may be pointing away from that point. So because of that, there would be some final error higher than the batch gradient descent when it comes to stochastic gradient descent. So something in between is the mini batch gradient descent, which is represented green color, which is having a rougher path than the batch gradient descent, but a smoother path than the stochastic gradient descent. So you can use a sufficiently large mini batch size so that it would be almost equal to the batch gradient descent, so that you can do it faster and uh, with the lower risk of diverging or having a higher final error. So that is the advantage of using batch gradient descent. Okay, okay, you can do one homework if you want, and if you have any questions, you can ask.